Hello and welcome to Chapter 12, the first chapter of Unit 3, which is going to be about characterizing stars. As this might imagine, or as you might imagine from the title that's Characterizing Stars, this is going to be less about the specific properties of a planet or the sun, as we saw in the earlier units, and more about the properties that allow us to characterize stars into different types of groupings rather than talking about their individual properties. Seen here is another Astronomer's Almanac, which goes through some of the discoveries that we're going to be talking about. And as you should notice, this is basically starting in the 1800s and still going up until 2004, and this book was only printed in 2019, but there have already been some major discoveries since 2019, according to my old roommates and my friends who... We are going to begin by talking about stellar parallax, which is something that is similar to 3D vision in our eyes, where as you look from your left or your right eye, an object is going to appear different places depending on how far away you are, or how far away you are from the object, where there is less of a change in how far, where an object appears if it is very close are very far away from you, and there's more of a change if it is very close to you. So using this, our brains are able to understand what depth something is, and by looking at an object at opposite ends of our solar revolution, we can also use this calculations, or use these calculations that our brains do to figure out depth, in order to figure out how far away an object is, just by looking at the angle between where we see it on one end of our solar cycle and where we see it on the other end of our solar cycle, just like 3D vision works with our brains. With our left and right eyes, you instead have far end and or far left and far right of the cycle of the Earth around the sun, giving you this parallax, or this stellar parallax, rather than just the parallax that we see in order to interpret depth in our brain. Using some trigonometry and some geometry, we are able to find that the distance from us to a star is 1 over the parallax angle of that star in arc seconds, and this is the parsec, the unit of distance called a parsec. If we're talking about light years, it's 3.26 over the parallax angle of that star in arc seconds, but I believe that a parsec is actually defined to be exactly 1 over that parallax angle in arc seconds. That's why it has par for parallel and sec for arc seconds. The brightness of stars measured without regard to their distances from Earth are called apparent magnitudes, denoted by lowercase n's. The brighter stars were originally said to be first magnitude. Those stars that appeared to be about half as bright as first magnitude stars were about said to be second magnitude, and so forth, down to 6 magnitude stars, the dimmest ones visible to the unaided eye. Because the stars do not appear with discrete levels of brightness, the system has non-integer magnitudes as well, such as 3.5 or 4.8. Objects with negative apparent magnitudes appear brighter than those with positive apparent magnitudes. The more negative, the brighter. Knowing how far a star really is and how bright it appears, its apparent magnitude, we can calculate how bright it would be at any distance. Absolute magnitude m is therefore the brightness of each star would have at a distance of 10 parsecs. Unfortunately, absolute magnitude has the same counterintuitive numerical scale as apparent magnitudes, but it is given by m, big M, is equal to the little m, apparent magnitude, minus 5 times log the distance in parsecs divided by 10. There is again blackbody radiation where an star that is similar but at a different temperature will give out different levels of radiation and have different peaks depending on that temperature. So a high energy star or high temperature star is going to have low wavelength but high frequency ultraviolet radiation, whereas a regular star such as the sun, I say regular because I'm biased towards the sun, is going to have visible light as its peak of radiation and release less light than the high temperature star. And a smaller star is going to release a longer wavelength, lower energy radiation, and it's going to release less of it. We have seen that astronomers can determine a star's surface temperature from either the peak of its blackbody or the strength of its various spectral lines. To make use of the diverse stellar spectra, astronomers since the middle of the 19th century have grouped several similar spectra into classes, or spectral types. According to one classification scheme popular in the late 1800s, a star was assigned a letter between A and P depending on the strength of the Balmer hydrogen lines, which is spectral lines referring to certain drops in energy in hydrogen in the star's spectrum. We see here this spectral sequence from O, B, A, F, G, and K, where the color for O is blue-violet, B is blue-white, A is white, F is yellow-white, G is yellow, and K is orange, and they have given temperatures and spectral lines, with the O class having ionized atoms, especially helium, and strong A class having strong hydrogen, some ionized metals, and so on, as you can see from just this table looking through the different properties of these different spectral lines depending on the blackbody temperature of the body. Around 1911, the Danish astronomer Einar Hertzsprung noticed that patterns emerge when luminosities of stars or their equivalent absolute magnitudes are plotted against their surface temperatures or their equivalent spectral types. Luminosity and absolute magnitude each indicate the total energy emitted by a star or other body. These two terms provide quantitative measurements in answer to the question, how bright is that star? Within 2 years, the American astronomer Henry Norris Russell independently discovered the same results. Graphs of stellar luminosity or absolute magnitude against surface temperature or spectral types are now known as Hertzsprung-Russell diagrams or HR diagrams. We see here HR diagrams of several stars, with the main sequence stars being that curve down the middle, and you will also notice that there are clusters of other types of stars which are dependent on some of the other solar classifications and help us actually aid us in actually defining these other classifications for these stars. These clusters are grouped into the main sequence, which is what our star is one of, giants and supergiants, as well as white dwarfs on the bottom end. You also have different luminosity numbers or luminosity classes, where the higher the number of the luminosity class, 1, 2, 3, etc., the lower the luminosity for a given surface temperature. Also, according to Kepler's third law and some physical considerations, the cube of the semi-major axis over the square of the period is equal to the sum of the masses for any given bodies or any given system. And for a main sequence star, a high mass means high luminosity, while a low mass means low luminosity.